Hello everyone, I'm Shomi Das from IIT Kharagpur presenting our paper Finding High-Value Training Data Subset Through Differentiable Convex Programming. This is a joint work between IIT Kharagpur and Hewlett-Packard Labs. As time goes by, the quantity of data is increasing in large amounts. There are several directions being explored in the area of subset selection. The research question asked here is, how do we select the most informative items out of such a vast stock? In general, this is a NP-hard problem. The word informative items can be used in different contexts. For example, when we want to reduce the number of features of a data point, we perform selection over features, terming it as dimensionality reduction. Summarization of long documents is yet another concept, while we can also think of a scenario where we want to find a subset of items that can help in keeping the test set performance at par compared to that of the whole set, or in other words, finding an appropriate set which best explains the test set predictions. We'll be looking at this third context of informativeness. This can be mapped to the usual setting of machine learning setup where we ask the question, how much does each data point contribute towards the test set performance? The answer to this question has been applied in several applications like explainability, debugging domain mismatch, fixing mislabeled examples, and more such. We'll look at some of them in our results section. With regards to this, there have been several works in the related literature, among which we have considered these four baselines. So, we come to our proposed method, HostCP. The high-level idea is to design a learnable subset selection formulation for selecting subsets and jointly learn the selection parameters along with the model parameters for optimizing the value function. The value function represents the algorithm which determines the valuation for being in that state, or in our case, in the selected subset. The problem statement is as follows. We want to maximize the value function of the subset such that the number of the elements in the subset is within a certain fraction of the total number of instances. We use test set loss as the value function, which should be the most minimum given an optimal subset is chosen. There can be other value functions too, like test set accuracy or expected return in the context of reinforcement learning. The considered related works take upon the task of evaluating instances in the following manner. They compute the influences of each training point on the test set performance that are basically the scores or values given to each of them as we are seeing here. In order to map this concept of valuation to subset selection, a very simple way is to take the top scoring elements. Now, do we see any problem with this approach? We can observe that similar instances marked by the same color, for example yellow here, are getting selected, leaving behind very close scoring instances like the ones in purple or red, thus decreasing the diversity of selection. To the best of our knowledge, while computing the scores, none of the methods compare the similarity of instances between each other, which can be a driving factor in the subset selection. We show here some examples from the real data, where out of 50,000 images belonging to 10 classes, only one of the baseline methods, DVRL, on being run to select top few images, ends up selecting mostly from the classes horse and bird. The after effects of such selection get manifested in the model performance, which will be presented later in the results section. Let us now look at the solution framework. We have a dataset D, which we pass to the selection framework parameterized by phi. The framework returns a value dependent on phi, which indicates the selectivity of the instances. The output of the selection framework is then passed to the machine learning model parameterized by theta, which can provide a one-step update theta hat that is dependent on both phi and theta. This goes as the updated parameter to the model, which receives the test set as the other input. The model parameterized by theta computes the training set loss and updates theta, while the model parameterized by theta hat computes the value function that is used to update phi. However, updating the value function with respect to phi is challenging since it has to pass through the optimization framework for computing the gradients. Further details will be explained in the later part of the presentation. We divide this structure into three parts. The first being selection, the second being updation of model parameter theta, and the third being updating of selection parameter phi. Now we shall explain each block and then connect the dots. For the selection block, the objective function is a minimization function on the dissimilarity values between the training set D and the subset to be found. This can be mapped to a facility location problem, which can then be relaxed to a convex linear programming problem. The idea is as follows. We have an existing set O and incoming set D. We want to find the representative of each element in D, which can either belong to the existing or the incoming set. So, we compute the similarity values between O and D and among elements on D. Now, an element of X from D can only be added to O if it's a good representative of the incoming set. This idea is illustrated in this formulation where D is the incoming set, O is the existing set, and this is the dissimilarity function which is represented as a distance matrix between the embeddings of a pair of instances parameterized by phi. One thing to note here is that this distance function used is an affine function which will eventually help us in differentiating through the optimization framework. We call phi as the selection parameter since it will be used in the selection of instances and later updated too. The details of this optimization can be found in the paper. The next part is updation of model parameter theta, which is done with the help of the training loss that gets defined here. We can see it uses the output of the selection framework and the model parameter gets updated using this particular training loss which gets backpropagated through the selected instances. The last part is updation of selection parameter phi, where the test set dt is used and the one-step update theta hat is used, which can be obtained from the training model. We compute the test set loss, which is the value function, using which we need to update phi. This update takes place by differentiating the value function as can be seen in the slide. Now, as we saw before, in order to reach phi, it has to be passed through the convex optimization framework. This is where we use the differentiable convex paradigm, which was introduced in a paper in NeurIPS 2019, where we can frame the optimization in a way using parameter affine functions such that the loss can be backpropagated through the optimization framework. It allows us to embed the solutions in the optimization framework as layers of neural network and also calculate the gradients. So, we can thus differentiate the value function with respect to phi by traversing through these two formulations at the bottom of the slide. Thus, the solution framework can be visualized in these three blocks which perform sequentially, thus giving subsets that are optimal for the test set performance. Next, we discuss some empirical results. We consider 4 types of datasets on different domains. In the interest of time, we show results on CIFAR dataset for the following applications. We present here the first application where we show how well the methods have been able to select the subsets which best explains the test set predictions. We see that with increasing fraction of selected instances, the test set accuracy keeps increasing and is also higher than the other baselines. The accuracy reaches close to that of the whole set at a fraction of 50%. An interesting observation is one of the baseline methods data shapely, indicated by DS here, reaches the same accuracy level at a fraction of 20% that host CP attained at a fraction of 5%. This denotes the presence of redundant elements in the baseline selections. We also show some intuitive examples where we can observe that the proposed method host CP selects images of varying classes like deer, bird, dog, unlike the baseline method that selects images of similar classes. The next experiment is that of mislabeling, where we follow this technique. We mislabel some random 10% of training data and run the selection algorithms to select a fraction k of instances. The hypothesis is that either the algorithms will not select the mislabeled data or it will give them lower values. So, we check the unselected or low value data, that is 1 minus k fraction of the mislabeled points. We fix those points back and train on the entire data. The entire data can now be a combination of clean and mislabeled points. We can observe here that with increasing inspected fraction of data, the accuracy increases and is comparatively higher than the baselines, denoting it is able to do an earlier detection of mislabeled examples. In conclusion, we proposed a technique for finding high-value subsets essential for better test-set predictions. We designed a learning convex framework for subset selection. We compared our method with the state-of-the-art baselines to show that the proposed method performs comparatively better, thus giving considerably better results. Thank you.